Welcome to the Water Data Podcast. In today's episode, it's a pleasure to host Professor Jay Famiglietti. Jay is a Global Futures Professor in Arizona State University's School of Sustainability. In this episode, we discuss the technology behind the GRACE satellite data. How does a satellite mission like GRACE actually see water that is buried deep underground? What can we learn from GRACE about global trends and hotspots in groundwater? According to satellite data, which regions of the world are experiencing the most depletion? And finally, we discuss the implications of use of satellite technology for the future of hydrology. And what can we hope from the GRACE follow-on mission that is now in orbit? Welcome to the Water Data Podcast, where we talk about science, stories, and systems that shape our water future. I'm your host, Veena Srinivasan. Every couple of weeks, we'll explore how better data and evidence can lead to better decisions and ultimately better outcomes for people and the planet. So whether you're a researcher, a practitioner, or just curious about how we can manage this precious resource, you're in the right place. Let's get started. Today, we have Dr. Jay Famiglietti, the Global Futures Professor at the School of Sustainability at Arizona State University. Jay's academic training spans geology, hydrology, civil engineering, and more, with a PhD from Princeton. And he's worked with several eminent institutions, including the University of Saskatchewan, the University of California, Irvine, the University of Texas, Austin, as well as NASA's Jet Propulsion Labs. Beyond academia, Jay has served at the California State Water Board and was a founding scientist of WaterPlan. He is best known for developing groundbreaking methods to detect groundwater depletion from space using the NASA GRACE mission. Jay, of course, is a great science communicator and a fellow podcaster. He previously hosted the show What About Water with Jay Famiglietti. Jay has won many notable awards, the Peter Eagleson Hydrological Sciences Award. He's a fellow of the American Geophysical Union, the Canada 150 Research Chair in Hydrology and Remote Sciencing, Berthold Dreiss Distinguished Lecturer, fellow of the Geological Society of America, and too many more accolades for me to list without us taking up the rest of this podcast. Jay, thank you so much for agreeing to do this at an ungodly hour of the day. Welcome to the Water Data Podcast.
Well, thanks so much. The pleasure is all mine. I really appreciate it.
Thank you. So the way we do this podcast, Jay, is that you, of course, have worked in many different areas, of course, global hydrology, which we'll talk about today, and measuring freshwater from space. But I was surprised to learn about your engagement with WaterPlan and corporate water stewardship. But we won't have a chance to talk about those aspects, but we will link them in the episode profile. So some of your work can be seen. But today I'm going to call this the Measuring Freshwater from Space and the Global Freshwater from Space episode. I think that there's a lot of attention to global hydrology in a sense of with the Global Commission on the Economics of Water kind of pointing out that even though water is a local subject, the drivers of local water are actually global. And so there's a need to measure and understand freshwater at a global scale, which is kind of where a lot of your work with the GRACE and other satellites has been. So maybe we can start with what got you into GRACE particularly. Why measure? It seems like a very unlikely thing to measure something underground from tens of kilometers above ground. So why was that kind of the holy grail when you started?
So, it's interesting. When you are doing your PhD, you think you're going to go off in one direction. And I thought I was going to be doing a lot of large-scale modeling and model development and taking the work that I did in my dissertation and trying to get it into climate models. But what happened in my case was that I started my faculty position at the University of Texas in Austin. And that's where the principal investigator for the GRACE mission was, Byron Tapley, and his very close colleagues like Clark Wilson, who was the chair of the geology department. And so during my interview, Clark Wilson said, "Hey, have you heard about this stuff? We're geodesists. We study the shape of the earth and the gravity field, and all that stuff is deformed and impacted by water. Maybe there's an opportunity for you here." And it sort of blew my mind. So I got into it. Then when I joined the faculty, I had also had a number of young colleagues that were about the same age as I was at the time, in my early 30s. So a good cadre of people, interdisciplinary. They were geodesists, they were engineers. I was a geologist, hydrogeologist, hydrologist. And so I kind of waded into it that way. I will say that I was a bit skeptical on the groundwater side. because they had, in the United States, we do these reports through the National Academy. And back then they were called the National Research Council, or NRC. And there was an NRC report on how gravity could be used to monitor all sorts of global hydrology and ice sheets and ocean mass. But then there were some lines in there about how, and we can use this satellite, and it hadn't launched yet, so this potential mission to track groundwater storage in the world's great aquifer systems. And I thought, wow, that's a bunch of BS. And my colleagues then started messaging on that. And I felt kind of a responsibility that, okay, I need to actually check this out. And so that's when I started working with Matt Rodell, who was my PhD student. And we started working on it. And it just turned out to be, over time, it proved to work a lot better than even we anticipated with our pre-launch studies, which were published around like 1999, 2001, 2002.
So basically, when you started, you were a bunch of basically techno geeks saying, we have this really cool satellite. Let's see if we can do cool stuff with it. And it didn't start off with saying, oh my God, we need to find a solution to the world's groundwater problem. It started off from saying, we have this tool. What cool stuff can we do with it? Which is legitimate, but that's what it sounds like to me.
That's pretty much it. And I will also say that the focus was much more on the ice sheet, Greenland and Antarctica, and on ocean mass. So the ocean mass component of sea level rise. And I think anything that the science team felt that they could get on any information on water storage on land, they just felt was sort of like, frosting on the cake. And that really all felt to me. And it just turned out, obviously it turned out to work really well and to be kind of a game changer in hydrology.
So then when you started working, what did it take for something like GRACE to be able to quote unquote see what's happening under the ground? What was that process like? Can you explain the GRACE mission first and then answer that question?
So, GRACE is a lot different than other satellites. When we think about satellites, we often think of a big camera or a telescope, up there in the sky, or a big thermometer or something, something like that. And GRACE, I like to say, is more like a scale because it's responding to the tug of gravity. So it moves up and down. As it orbits around the Earth, it moves up and down in response to places that are gaining or losing water mass because those places either exert more or less of a tug on the satellites, moving them up and down, just like a scale would move up and down.
And it's a pair of satellites. So it's basically
two satellites.
Differential.
Yes, right. It's two satellites. They're up at 400 kilometers. They're separated by 200 kilometers. And they're in a near polar orbit, which means they roughly are orbiting over the poles. So they're effectively sweeping over the Earth. And when the first one comes in a place that flies over a place that's had a big mass increase because of, say, a huge storm or something, then it gets accelerated, moves down a little bit and accelerated towards the mass and then relaxes back to its orbit. And then the second one comes in, it does the same thing. So it's the relative position, the absolute position and the relative position of the satellites that are used to map the water storage changes.
And how frequently does it go around?
It's about 16 overpasses per day. And it takes about a month really to make a complete gravity field to keep the errors down. So anyway, then, you asked the question then, how do we get to water storage changes and groundwater storage changes? And so the first step in that process, which started before, we started working on this in, say, 96, 97, again, with Matt Rodell, who was my PhD student, is now at NASA Goddard Space Flight Center. We did a lot of pre-launch sort of feasibility studies. And then in the early years of the mission, really trying to compare to observations on the ground, what were we actually seeing? Were we actually seeing water storage changes? So compared to observations on the ground, compared to models, and we were reasonably confident. We were actually quite confident. And, the more the mission went on, the more data we collected, we gained a lot of confidence. But then there's the issue of how do you get to groundwater? And so what GRACE senses is the change in all of the mass, right? All of the mass change in a region. It turns out that most of that is water, but we don't know what kind of water. And so then the challenge in a region is to figure out, using other data, how much of the mass change that we see from GRACE is from snow, is from ice melt, is from surface water, is from soil moisture. And that's where, the errors come from. And that's the challenge. You have to put together around the world, wherever you're working, it could be global, it could be regional. You have to come up with these other data sets. They could be observations of snow and surface water storage. They could be from models. It varies from place to place. So the work that we do here in Arizona, the work that we've done in California, we were able to collect a lot of data sets on the snow and the surface water and the soil moisture. But if we try to do a global study, we rely on models and satellites because we want to be consistent. So,
right. Let's unpack that a little. So I'm going to ask some really dumb questions. So one of them that's always kind of struck me is, if you look places like China and India, entire cities have come up in some places where they went from almost being nothing on the ground to like 10-story or afforestation or deforestation. There's other types of mass changes. Are those negligible or are those just easily visible from space?
well, they're easily visible from space from other satellites, but in terms of mass, they're surprisingly not that great a contribution. And so numerous studies on all aspects of the things that you just mentioned. And as well as, pumping oil and things like that. So water is everywhere.
I mean, it's lovely to hear as a hydrologist, but also surprising.
But the biggest things that have to be corrected for are movement of magma in the mantle. And so, because that's quite heavy and it's also everywhere. So in some places, it's happening on the time, still happening on the time scales that Grace is making the measurements, in particular up north around Greenland, and earthquakes. Earthquakes can, really displace a lot of mass in a short amount of time in the time period that Grace is making measurements. So those are the big things that need to be taken out of corrected for in the data.
And is that because there were a lot of geodesy scientists? What do you call people who study geodesy? But people who study the shape and gravitational field of the Earth, they do all of that stuff, and so essentially those corrections are pre-made for hydrology to come in and
yes, they are. Exactly. Okay. Thankfully, so early days, we had to work with the team to try to figure it out. I mean, back in the late 90s and the early 2000s, we were all sort of working together trying to figure out what we were seeing. And then at some point, I think after the first couple of years, then the science team, there are people that work on all kinds of corrections, atmospheric corrections, there's tidal corrections. There's the mantle convection, post-glacial rebound, so called GIA, glacial isostatic adjustment. So all that stuff is, and of course, it's always being improved. But yes, we've sort of, I wouldn't say we're in stovepipes, but we have our tasks.
So great. So those guys have figured out all of the other stuff. So what's left is the water pieces, which are significant, and that's left for the hydrologist to kind of partition. So can you then tell us how you partitioned all the other pieces and then were left with groundwater?
So if you are given a map or a time series, so we look at it in two ways. We look at the maps of the monthly changes, and as the years go by, we look at the trends or the emerging trends, and we look at the monthly time series. So we see the ups and downs, and lots of places, it turns out, we didn't actually really realize this before we had the GRACE data. Most places around the world, except in the drylands, have a very strong annual cycle. So then the challenge becomes understanding, if you're in the Amazon, okay, how much of this is the seasonal flooding? How much of this is groundwater? If you're up north, or if you're in the mountains, how much of this is snow melt and glacial melt? And so it really comes down to, if you look at a region, you pull together the best available data or colleagues that want to work with you that have the expertise. So you really can come together and say, oh, okay, we're in California. We've got, these great snow data. We've got all these reservoir data and stream flow data. We don't do such an awesome job on soil moisture. We tend to rely on models. That's everywhere. That's not just California. And then we have groundwater well data. And so we, make the calculations and compare to the observations. And that's, we go on and we try to improve. And we're still trying to improve. And it's been, 25 years.
Right, of course. So one thing that I saw in your papers is that when you started, like the raw GRACE data, that sort of three different groups across the world kind of disaggregate it, so to speak, to arrive at a groundwater signal. And they arrive at slightly different signals in different places, depending on what their models have and what assumptions they have and what training data sets they have. So were there big differences across? And if so, where were those differences or the uncertainties the biggest in the world, spatially?
Well, so first of all, I think some of the differences come from the GRACE processing centers. And so there are still really three big ones. So NASA Jet Propulsion Laboratory and Goddard Space Flight Center and the Geophysical Research Center, GFZ, in Potsdam. Early on, there were differences there, and the teams are always sort of cross-comparing. And sometimes people would use an average, and sometimes the different centers are rather arrogant, and they'll say, "Well, mine is the best, so I'm just going to use this." And that was certainly the case at JPL. There was a feeling that ours is the best, and so don't worry about it. And so that's sometimes we do that. Sometimes we look at the average. I mean, that's the beauty of research, is that there's more than one way to do these things. And so, we write our papers, we compare with each other, we go to meetings, we have conversations, and then we, go back to it. Sometimes we come together and we try to resolve the differences. It's hard too, because we're not like super well funded. So it's not like we can just like get on a problem and say, where I'm working now at Arizona State. It's not like we can stay on that forever because we don't have unlimited funding. So in an ideal world, we just keep working together, and try to, make it perfect or as good as we possibly can. But we don't have the funding to do that. So, we come together, we write a paper, we compare to observations on the ground, we talk to our colleagues. Maybe they write a paper and maybe there's differences. And sometimes we can come back and talk about it at meetings, and sometimes we don't. And so sadly, it's an imperfect world. But I would say...
But where are the differences kind of significant in your view? Today, after 25 years, are there still places where somebody is saying the trend is 2 centimeters a year and somebody else is saying it's 4? No, it's sort of...
No, I mean, within a percent, I would say it's probably within about, 20%. And for the kind of large scale work that we're doing, I'm fine with that. If it's plus or minus, 10% from a mean, they're not great anymore. They're not great. And in the early days, they might have been bigger because of the processing center might have used a different glacial isostatic adjustment correction, right? Or they might have used a different, tidal correction. So we were getting a lot of differences that way. And one of the first papers we wrote, we didn't have the GIA correction in there. We actually presented a poster at AGU where the trends were the opposite. We had like the land storage going up and the ocean mass going down, and like our colleagues saw it and they said, like, we need to work together to figure this out. So no, I think things have really converged, and now it's the differences are smaller. And we all agree that things have to get better. We're all trying to work with other, doing downscaling. We're trying to bring in other sensors like radar and GPS. And I'm confident that, the next decade, assuming the GRACE follow-on keeps flying, and then we've got another GRACE mission after that.
When does that come on?
That's an excellent question. So we don't know about when the GRACE follow-on will, end its life.
Right.
The first one was 15 years. Mm-hmm. And this one launched...
That was
2002 to 2017. And then the follow-on launched in 2018. It's still going. And then there's the plans for the next GRACE mission. And I am not actually certain of whether that's been approved by NASA. We are undergoing a decadal survey in the United States, beginning this process of the decadal survey. In fact, just had a virtual workshop yesterday on some priorities. So at least in the US.
What are those priorities then? So now,
that's what we're trying to figure out. They're community priorities. Yeah. Okay. Yeah. So we don't know.
But broadly, I mean, where are the limitations? So of course you want to keep getting data because we keep depleting groundwater, and that's forever. But in the sense of, if we had to say, where are the limits of the current GRACE mission, and what would be aspirations for the follow-on to the follow-on, whatever it's called, what would that be?
So the limits are always going to be the spatial and temporal resolution. That's just because of the way gravity works. There's probably some limits on processing as well that can help us get to higher resolution. Right now, most sensors have a 25-kilometer product out there. But yes, the native resolution is about 3 degrees. So anything that could get us to 100 kilometers or 1,000, anything that can improve that resolution in space and time weekly, I think would be great. And it's always a trade-off with any of these satellite missions, right? It's the trade-off between the cost and like the applications, right? And the cost really goes up exponentially as you try to do these things at a higher and higher resolution. So that's where, a lot of the science team and these priorities that I just mentioned, those trade-offs are always going to be compared within NASA and within the research community to sort of make the best recommendations possible, in our case, to the United States Space Agency, which is NASA.
If you're enjoying this episode, don't forget to subscribe and explore more conversations on the channel. Share this episode with your colleagues, friends, or anyone interested in water and sustainability. And tell us about yourself in the comments. Are you a student, a professional, or just curious about water? Let us know where you're listening from, and if you'd like to suggest a guest or topics for further episodes.
So let's just come back to, for a second, the resolution and sort of, it's very clear the value of what GRACE brought to the world is kind of incredibly clear, right? On one hand, it allowed people to kind of at least constrain their hydrological models, but that's a very hydrology, it's what the hydrology geeks kind of get excited about. It's very difficult to get politicians to say, we need something to constrain our mass balance. It's just not an exciting headline. But the Rodell et al. Paper, which was the paper in Nature from 2009, that was incredibly effective and incredibly impactful because, and from an Indian perspective, that bright red dot in the entire planet to show this massive, massive center of groundwater depletion in northwestern India. It's a early warning system in some way, but then it's too coarse to use directly as in policy. Given the course resolution, if I had to ask you, what would you say is kind of the ambition for GRACE in its current form? That would appeal to a lay audience.
Yes, okay. It depends on who you are. And to some people it is, I want to improve my model. And to people like me at this point, after, working on it for the whole, project, I mean, it's been 30 years because we started in about 96 or 97 pre-launch. And so for me, the real goal is to impact policy and to impact policy at, state, regional, provincial, national, and global scales. And so you're right. It's easier to do that, in the UN, not easy to do, but easier to, actually impact any policy is actually quite difficult, but an easier story to tell at the larger scales. And so it's when you get down to the smaller scales that you really have to be strategic about what your narrative is, what you can and can't do, what the current state of the art is. And, a recent example is we had this paper come out on the Rio Grande, which is transboundary, at the border of Texas and New Mexico and, southwestern U.S., and the New Mexican officials just jumped all over it and actually just asked for a little virtual briefing just last week. So really trying to understand what's going on. And we're, able to get down with our 25-kilometer data. And then we're doing some downscaling too, which goes down to 1 kilometer. It hasn't been published yet, so I don't want to talk too much about it, except that so many groups are doing that. So that we're getting better at impacting policy. You had mentioned California. California, at that time when I was there and had this work coming out, it was a really, really severe drought. And so especially in this time frame of 2011 to 2015, it was really terrible drought. And the work that we were doing, even though it was fairly coarse, you take the Central Valley and or the middle part of California, we carve it up into, the Central Valley system, but it has 3 parts, like the Sacramento River part, the San Joaquin River part, the Tulare Basin part, and they're still very coarse. But yet it was enough to give the governor, the confidence to put the Sustainable Groundwater Management Act on the ballot. So, it has importance in different ways. Can it help us make a decision now in Arizona, in one of our so-called active management areas around Phoenix? Not yet, but we're working on it.
So I have a question for you on this. There's this idea of a canary in a coal mine, right? So, the canary drops dead, you probably don't have enough oxygen. I was wondering, nobody tries to say, let's breed canaries to manage coal mines better. So in a sense, what GRACE does, really bad analogy.
I love it.
what Grace does is that bright red spot cannot be missed, right? It's telling you this place is losing large volumes of water consistently over decades, which is really important. It doesn't necessarily have to play the role of now it needs to tell me how to manage better, but it should ideally tell you go and put lots of piezometers there and manage that place better. So maybe it's a wrong ambition to have to say use it for local management.
It could be. It could be, but there are those of us that are still going to try, myself included. Like we want to, that's the fun of science is sort of think about how we can make these products better. I agree with you. I mean, the real power in Grace is almost, more at when you look at the global and regional maps and you see what's going on, and it is really becomes undeniable. And to me, that's always, it should be, and I know it works this way because I'm in contact with the governor's office here in Arizona as well. It's enough confidence for the governor and the attorney general to look at those maps and say, we knew this was happening. And now, right. So there's really no denying that this is happening all over
you're
Arizona.
losing enough water to change the gravitational field of the Earth. So
that's right. And things like impact sea level rise and
change
the Earth's rotation. So there's a complete picture there. So I agree with you, but there's always going to be those of us who, of course, we've got the NISAR mission, which is joint with India. We want to figure out how we can combine that. And that's research too. So never say never, but I agree, at least in my, career, that's been the most success is at painting that regional picture. I do want to say though about what things might be deniable or undeniable really depends on who you're talking to, even at the elected official or ministerial level. And I had a really interesting experience in Bangladesh. We went there was right before COVID, so it must have been the dark ages, 2020. And we're in the Minister of Water's office and showing, it was probably like a deputy minister, and showing them like, okay, you know what? Like at this point right now, like your region in Bangladesh is actually the worst in the world, right? In terms of groundwater depletion. Had no impact.
It didn't?
No, he didn't. This person, I don't remember his name, didn't really care and just kind of shrugged his shoulders and said something like, well, we have satellites, so we'll see it. And by satellites, by the way, he meant drones. So it really depends on who you're talking to and what their priorities are.
Right. So while we're in the subject of Grace kind of telling us and the story you just said, what did we learn from Grace? Which parts of the world are the hotspots that are losing the most groundwater by volume?
Yeah. So I think a lot of the information comes from the global trend map. Mm-hmm. And until our 2025 paper came out, I would say the following. We now see very clearly that the high latitudes and the tropics are getting wetter. The wet areas are getting wetter. In between, the mid-latitudes are getting drier. And we also see these hotspots for things like glaciers melting in Alaska and Patagonia and around the Himalayas. And drought in Brazil, and groundwater depletion in the world's major aquifers with major hotspots in India and Bangladesh and California and the Middle East and China, and these places really, really popped out. It's mostly the same now, except for that what I said still holds true in the current map, except now that the high latitudes are not getting wetter, they're getting drier, and we're pretty sure that's because of ice melt and permafrost thawing. So that's it. It's this global picture of sort of the background with the hotspots for too much or too little. And of course, some of the flooding stuff is showing up too, especially now in our latest map in East African Rift Zone.
Does the flood show up as well as groundwater because flooding is so much faster a process than groundwater depletion? So in a sense, is it there in that 1 month average?
It will show up, but it's a good point. It's a little bit more of a flash. And so it will show up if you were saying, and a lot of times we'll do this, we'll do animations and look at the monthly data. So it'll show up. Then, you can imagine then if the floods are actually increasing then over time, then the region may actually increase in water storage, total water storage. And then you would start to see it in the trend stuff. And that's what we're seeing in East Africa.
Right. So while we're in the subject of hotspots, let me complain about being in southern India, we feel very betrayed by grace because, of course, much of peninsular India is hard rock aquifers and there's no storage. We have a massive groundwater depletion problem, but obviously, because you don't have large alluvial aquifers, you're kind of emptying and filling, rapidly. But we sit on our wells here are, 1,000 feet, 1,500 feet deep. But of course, there's no storage. You're just chasing the few particles of rain down to that depth. And it's not obviously fair to say that Grace should even measure that because it's not a significant volume, but it is a different kind of groundwater depletion problem. Is there a way to kind of to characterize this and say, okay, you really need to pay attention to Punjab and the northwest of India because that's losing, obviously that's a long-term storage problem, but you still have groundwater crises in other places. They just manifest very differently. How does one kind of handle that? Does it not need to be a part of the global conversation?
Do you have our episodes running in the background? If you're curious about a technical term that we've used or an acronym we've forgotten to expand, we have on-screen explanations that we offer on video.
No, I think it does need to be a part of the global conversation. Of course, Africa is a lot like that too, with a lot of its basement, right, fractured rock. And I apologize that, we can't, that you're not getting the attention. But okay, so what can Grace see and not see? I mean, it has to be a significant mass change. And if the mass change isn't really significant enough to, affect the satellites, then it doesn't get seen. But you're right. That doesn't mean that it's not important. And that's where I think, the local scientists need to come together and explain why it's not being seen. And, that may be a case where you just need to use more groundwater, or you need to use more groundwater wells, more observations, and tell the story in a different way. Because, at the end of the day, satellites can't do everything. So, yeah, I mean, that's also why. So thank you for pointing that out about peninsular India. And again, that's why we don't see a tremendous change in a lot of Africa for the same reason. Maybe this, there's the global, like IGRAC has the global groundwater, like the, sort of hydrogeology maps, and the combination there of showing like, okay, what does the hydrogeology look like? And what do we see from Grace? And, okay, that's why. It may be a little change over here actually means a big change for that region. So it's a difficult problem.
It actually doesn't show up very neatly in static water levels either for complicated reasons. I mean, partly because there's a survivor bias problem because only, the wells that dry up actually drop out of the monitoring data set. And we did a paper in Geophysical Research Letters on that. Nonetheless, I think that it's interesting just to say what we mean by depletion and what we can measure from space and then what we need to measure from ground. But really where in these hard rock systems it shows up as energy kind of increases, significant energy increases, and then significant, of course, loss to farmers because they have to drill in these really very difficult terrains. Anyway, so let's kind of move on to kind of the causes of the losses for a moment, because what we are able to see, which is massive losses in particularly alluvial systems, because that's where you're going to see them. How much of that are we thinking is because of climate change and versus just people aspirationally pumping more, as they develop, as economies develop?
I've always found that difficult to separate because big parts of the world are getting drier, right? In our paper that came out in July 2025, we're showing that continental drying is expanding and by 2 times the area of California each year. And so, of course, when it gets drier, we use more groundwater. So it's really, really difficult. So let's put it this way, if there were no climate change, we'd still be seeing a lot of groundwater depletion for different reasons. It's a free resource in a lot of places around the world, and some places you don't even have to pay for the electricity to pump it. So it might be driven by food production, it might be driven by export. So even in the absence of climate change, we would be seeing this groundwater depletion. Is climate change making it worse? Absolutely. These dry areas are definitely getting drier. It's getting hotter. Look at the Western U.S. or around the world, stream flows are drying up. Colorado River Basin, great example. Arizona, California, Nevada in the United States, they're going to see some serious cuts in their Colorado River water. What does that mean? That means they're going to have to use more groundwater. So we never really have a sort of, sharp percent, which is this much is climate change, this much is drought, this much is natural variability. But what we say instead is that they're so interlinked that, it's practically impossible to separate them. We could do some of it with models. We don't do so much of that. I wouldn't say it's unimportant. We understand what's happening, and we're just more interested in getting the message out about the rate of groundwater depletion and the rate of drying. All that said, most places that we look, and we see in most of the dry parts of the world, we usually see, when we see a trend, a negative trend, a decreasing trend, usually 2/3 of that or more is from groundwater.
Right. Well, you could, I guess, see where it's accompanied by an expansion in area versus where it's fundamentally like the northwest of India, which is, it's 400 mm of rainfall, 500 mm of rainfall, 1200 mm of evapotranspiration over decades, and complete disconnection between irrigation area and rainfall, which is basically then all developmental. Versus in other places where you're really running faster to stay in the same place, which is that your climate's gone drier and then you're pumping. But I think what you're saying is it's complicated because they're interlinked. And so we kind of have to wait to kind of completely be able to. And there's a question about, is it even worth it, to bother?
I'm more focused on, as we said earlier, I'm more focused on the protection. Both of these things are happening, right?
Right.
And the only part we can really control is the human part. If we all came together and, suddenly reverse climate change, fantastic. But, in my lifetime, I don't see that happening. And so I see the real lever as being groundwater protection, groundwater policy, and regulation.
And of course, groundwater is particularly important because in an era of climate change, it's also the buffer, right? It's the equivalent of burning up your insurance policy before the fire sort of thing. So while we're talking about this, I was wondering whether you could give us a couple of examples. Can you walk us through one of your examples of how the data was used, it went into policy, and then how it's actually being used in different ways to actually move a needle or improve? Do we have any happy stories? Is the California Groundwater Act kind of a success story yet?
Good question. So let's see, good success stories. Well, the integration of the GRACE data into the drought monitor, the National Drought Monitor to the United States, I think is great. So that's a huge success story.
Can you explain that for our audience?
Yeah, there's a version of the National Drought Monitor, which is weekly maps that come out, and lots of things are considered, and even some of it is subjective. You've got different agency representatives, different data streams. And one of the data streams that's now been incorporated for a long time is maybe for about 10 years now is the GRACE data. And that's all through Matt Rodell and the NASA Goddard Space Flight Center. So that's, unquestionably a success story. The work that we did in California was much more like background, right? Inspirational. And it wasn't just the science. It was the science communication, of which I did a lot. And that could have taken the form of writing opinion pieces, that is, national news shows. And we got a lot of attention, in part because it was at the Jet Propulsion Laboratory, which, the media loves it because it sounds like great technology.
Rocket scientists, literally.
Yes, exactly. And so, and it was, at the same time that the papers were coming out, and not just California, but, Middle East and global papers. And it's also very close to the major news bureau. So they're right there. So it's kind of like a perfect storm to do the messaging. And so the messaging was really, really important. One of the things that is cited routinely by it's called the State Water Resources Control Board in California, as having a huge impact on giving the governor's office the cover, the political cover. What did they say? We took the conversation out of the State House and, into the public. I mean, I literally had a taxi driver say one day, I mentioned that I was going to the airport. I mentioned that I was going to some water conference. He said, "Oh, did you see that image that was in the paper today of like the 3 images of California going from like wet to dry?" I'm like, "Yeah, that was mine." So it was very far, very far reaching. Efforts to use it for monitoring routinely are much more difficult. And it comes down to funding. And I'll say very clearly, I had been upset with NASA I'm happy if you want to keep this in the in the podcast. I've written a couple of proposals with the State Water Resources Control Board in California and the Department of Water Resources to use GRACE as monitoring. They're not even, the last one wasn't even invited. It was a pre-proposal. It wasn't even invited to a full proposal. Also, when I was at JPL, we set up something called the Western Water Applications Office. The same thing. I had the State Water Board was saying, we need to use your stuff to help us monitor how the Sustainable Groundwater Management Act is doing or will do. We need to work together. And the people in charge of the Western Water Applications Office just said, oh, that's not important. They're not an important stakeholder. So sometimes the people who are making decisions about our funding don't really understand what we're trying to do. And that part is really, really frustrating.
Why did they think it was not important, in the sense that it is important? No, but is it understanding of the value of GRACE or the value of groundwater data at all? Because were they saying we have a lot of piezometers, that's enough? Because you can still see that if you can see improvements in the gravity signal, that means you're doing well. I mean, that's the good thing about GRACE. The fact that it's a coarse signal is actually its strength in some ways, right? Because it's such a strong signal.
If you find this episode to be valuable, please like the video and check out our other show on this channel, The Well Labs Show. And don't forget to subscribe to the Well Labs YouTube channel.
So in the case of the first California proposal with the Western Water Applications Office, the person who was in charge wasn't even a hydrologist, was really like a business, like an economist. And, where they were looking for sort of cases where, almost like a business case. So completely just had no idea what I was trying to do. There are very few times, Mina, in my career where I've completely lost it at work, and I lost it. The other one, I haven't actually been able to communicate with NASA about why did you not think this was important? And one of the reasons that I wasn't able to do that was that NASA was shut down because of the government shutdown. And then a lot of the NASA folks didn't come to AGU where I thought I would see them. So I will pick it up. But again, I asked the question, like, what is going on? How can you, this stuff cries out for funding. It's like the biggest use case in the United States. What are we doing here?
There's a reason this is called the Water Data Podcast and not the Water Model Podcast, right? Is because we want to highlight the value of information in and of itself, right? And I wonder whether we as hydrologists have done a disservice by not recognizing that investments in data have high return on investment, right? Eventually, you do models, and of course, GRACE is assimilating, and it's very complicated data, but at the end of the day, it's producing a raw data set, which is itself telling you something about the state of the earth. And the question is, if we could just show that has actually, making those investments has massive returns to the economy. And I wonder whether we should be just doing more of that. India is a much more extreme case, right? Governments come with exactly this argument saying, show me why this particular agency, how this particular agency is going to make money off this data. Problem is the agency doesn't make money, but the economy saves in other places. Case for investment in public goods is that, lives are saved, insurance companies save money, farmers don't lose as much on their crops, they don't lose as much on, drilling. And the problem is the benefits are distributed and the costs are concentrated. And I don't know, I feel like we don't make enough of a case that there is. I actually think there is a return on investment, but I think highlighting that has its own value.
I think you're absolutely correct. I think a lot of us don't have the time, don't have the expertise to figure out how to make those cases. In some cases, we need to work, and we should be working with economists and who can help us really characterize and quantify the value of making that investment. I couldn't agree more. And I agree. We're terrible at it. And we just, people like me, it's not that I don't want to do it. There's only so many hours in a day.
Yeah.
And there are
you can do it. Somebody else.
I can't do it. I don't have the resources to pull together. It's hard to get money to do even the most important things.
Yeah.
And so it's really, really hard to do. And it's an imperfect world. So someone like me, I'm a professor. I need to teach classes. I need to supervise graduate students. Only a few of them are working on GRACE. And so it's an imperfect world.
Of course. Of course. So let me pivot one more time to kind of understanding. We've talked a lot about grace, but of course, your career hasn't just been about grace. You mentioned INSAR, the NISAR satellite with India. India and France together are launching another satellite called Trishna, which is focused on evapotranspiration. So there's a whole bunch of new satellites being launched, including bilateral investments by India and other countries. What is kind of the ambition of global hydrology now, looking beyond groundwater at all of these other different satellites? How are they all going to talk to each other, and what can we kind of look forward to?
Well, I think of that as the Holy Grail. And the idea that you can ingest all this asynchronous information, say, into a model or models and have the best available observing system, I think it's entirely possible. And then we can throw in some machine learning and make these things digital twins to help us improve, right? So the process understanding can be improved over time. So it becomes a living entity. I think that we can look forward to that. But that is easier said than done, again, because of the investment. If this were a private sector endeavor and this were like, okay, I've seen, my son works in autonomous vehicles. I've seen the investment in autonomous vehicles, which are doing the same thing, by the way, right? They are asynchronously assimilating all kinds of information and making decisions in real time. Okay, I've seen the investment. And what we have is about 0.001% of the billions and billions and billions of dollars. So I think we can aspire to that. It is a noble ambition. We need leadership, we need political will, and we need to convince, right, our governments that this is a worthwhile investment using, right, the return on investment scenarios that we just talked about.
You've mentioned in a few of your papers the GLDAS models of NASA. And the way I've understood them, which is why I want to unpack a little bit about what you're saying, the way I understood them is sort of you have these big global hydrological models. They keep predicting soil moisture and weather patterns and so on and so forth. They obviously don't always get everything right, but then they keep kind of correcting or getting retuned on a day-to-day basis with all the best available data. Is that what data assimilation means? Or because you said something slightly different, you said we can use it to understand processes better. So I guess my question is
that's the future. That's the future.
Got it. Because
so what we're doing now is exactly what you said. We correct the models with data assimilation, and then we, keep going.
If you're constantly correcting, how far into the future can you currently predict with a GLDAS model? Because after a few months of prediction, like even if you want to do a seasonal prediction, things are going to start drifting, and you're not going to have the data to assimilate.
Right. Okay. So that's a different problem. So the GLDAS and models like that, global hydrological models, do a great job on the historical period up to the present. Then anything after present becomes forecasting. We can use the models for scenarios. They're excellent in that. But when it comes to prediction, I think they're best used to initialize weather forecasting models, right? And then that becomes a different problem. Then that's a weather forecasting problem. And it's not
that's a short term. That's a 7-day or a 10-day weather forecast.
Yes, right? and as we know, that's a difficult time frame. But that is a time frame where it's a separate field. It's not work that we do in hydrology, but that's a time frame where that community thinks that machine learning will be super, super helpful. Right. And all I was saying about integrating all these things together is that in using machine learning is that we have the opportunity to do even better and to have maybe more realistic scenarios. If we want to do scenarios of, say, the impact of losing Colorado River water in the southwestern U.S., what's the impact on groundwater? We can try out different policy scenarios in our models and get a range of scenarios that might be more realistic. That's all I'm saying. The forecasting, that's a different thing.
That's a different. So what you're saying is it's a traditional hydrology model that you're modeling all your physical processes, but you just have a lot more data to constrain the model. So you're saying that I know what soil moisture was on that day in this part of the world. I know what stream flow was. I know all of these different things because I have all these different satellites measuring all these different things. And that's giving me confidence in my model's predictions because it was able to replicate all these different processes that were observed in the world. And that's giving me confidence that it will hold going forward. And therefore, I can run these scenarios on it.
That's exactly right. And then it's also important to remember that with remote sensing, we couldn't do it because we'd have maybe spatial gaps, we'd have temporal gaps. And so that's why we have to bring the models and the data together, because it's sort of a perfect match.
That's super, super useful. I was wondering whether, Jay, you could give us a little bit of an insight on one thing in all of these 30 years that really surprised you in terms of process. So, in the sense, you had a certain way of running the algorithm you missed, or key thing that was happening in some part of the world, which got you to predict something wrong. I was just trying to understand how valuable some of these data assimilation things are, where if you left out one data set, you were actually getting something off. I was wondering if you had an interesting story around that.
Well, it's not quite that, but I will say that probably the most surprising thing in my career has been the recognition of the widespread impact of groundwater depletion, the realization that it is a global phenomenon. And, you read it, and, Lenny Kanishka had some papers on it in the early years, and you read it and, you think, oh, yes, this is a big deal. But to see it emerge in the GRACE trend map over a period of a few years, because it was while we were improving the technology and everything. I like to say it was like in the old days, you go into a dark room and you would watch a photograph develop, or even, a Polaroid, you kind of watch it slowly develop. That's sort of what happened. And the first thing to emerge was India, because it was so big, right? So it was like the first sort of, the signal is emerging from the noise. But as we got a handle on the noise and could shrink it down, then we started to see like, oh, okay. Now, like we saw this thing happen in California. And then we realized, okay, like here's this red spot here. That's India. That's groundwater. Here's California, right? That's groundwater. Well, here's the High Plains Aquifer. Here's the Middle East. Here's the North China Plain. And to me, that was the eye opener of my career, and actually the thing that sort of put me on the path to science communication.
Fantastic. As I said in the introduction, you've had your own podcast. You've really kind of walked the walk, so to speak, on science communication, appearing in documentaries, writing op-eds, all of that stuff. And I hope that we will, of course, link some of those in the episode page. But I hope that's an inspiration to younger people to kind of say that, very deep science can have impact, but it really needs you to get savvy the way you've been with your career and be willing to do all of that. Do you feel that's been rewarding, or do you feel like you paid a price for it in having to give up some of the time spent on science?
No, I find it to be very rewarding. I think it's very time consuming. Think about the number of those things that I've done. Some people would look at that in terms of like, well, I could have written 10 more papers. But I have found universally that the impact of those opinion pieces and the readership and, the raising of awareness is so much greater than any paper that we might write. It's fun to write a big paper and have it, be recognized and, have people thinking about it. But it's just a different thing when you're communicating to the public, or, decision makers are reading this stuff. I find it really, really rewarding. And I feel like it's been the most impactful work that I've done. I think one of the reasons that it's been impactful and rewarding is that we've done the science. So we're not just like talking about stuff. We're talking about like from a place of deep research and deep concern because of the research.
Fantastic and super inspiring. Jay, it's been a fantastic conversation. What I'm going to do towards the end of this is, which I do with all of the guests, which is we have a lot of young people listening. And I was wondering whether you could kind of leave us with inspiration if you were starting your career again. Obviously, you've seen 2 whole missions of GRACE and you've been there from the very inception. But we have a whole brave new world opening up. What would you be excited about if you were starting your career now? What skills would you invest in? What topics would you explore that you feel are rich for experimentation and exploration? Leave us with some advice.
Sure. First of all, I want to thank any young people who are out there and encourage more young people who are out there to consider pursuing careers in environment, in water, in climate change, in sustainability. We really need your help and your leadership because we have tremendous challenges ahead. I think most students today are going to be well served by really understanding not only the science, but like we talked about, machine learning and AI is extremely important. understand its limitations, but harness its strengths and think about how we can bring these things together into, real digital twins, not just to use a buzzword, but to really understand that a model, it's not just a model, and it's not just remote sensing, and it's not just observations on the ground. It's this sort of living digital representation of what's happening, and really strive to make those, in the way that we always have in hydrology, really strive to make those work well. And then make sure that the people who need to know about it. And that could be your elected officials, that could be your water managers. And so invest in science communication, invest time in making clear presentations. It's so important. Try to get out there and work with your supervisor if you're in a university. Try to make those connections to, do some government briefings or do some public presentations, even as a graduate student. Go to the church group, go to the school group, get that practice speaking in front of people and communicating. Super important.
Fantastic. I love the inspiration, but also just the call to action on do science and then communicate the science. Thank you so much, Jay. It's just been a lovely, lovely conversation. Thank you so much for doing this.
Well, thank you. I really, really appreciate it. It's been a lot of fun.
Thanks.
That's it for this episode of the Water Data Podcast. Thank you for listening till the end. If you enjoyed the conversation, please subscribe to the Well Labs YouTube channel and share this episode with your friends and colleagues. You can also find the Water Data Podcast on all podcast platforms. Until then, stay curious and stay connected.